Okay, guys, so for this last one with lesson 47, we're going to focus on some of the basic types of reactions for organic compounds. So there are 7 we're going to focus on here, these 7 right here. So we're going to go through each one, look at some examples and the practice with them before you guys work on your worksheet practice on your own. So the first one in here that we're going to focus on is called a substitution reaction. So again, like it says here, there are several types of reactions. There's even more than we're going to talk about here today. This is just a basic introduction. But a lot of times they have to do with breaking some of the double bonds, changing functional groups. And so there's tons of different reactions, different pathways that can occur that we'll learn even more about next year. So this first one, the substitution, the basic definition of what's going on here is you're substituting something. So you're replacing usually the hydrogen atom of an alkane, so it's got all single bonds, with a halogen, okay? So essentially, if we look at kind of the pattern here, you have an organic reactant. It's always going to be an alkane, meaning it's a saturated hydrocarbon, so it's all single bonds. Like if you look at the example right here, all of them are single bonds. And your other reactant is going to be a halogen. So it could be fluorine, like this example, it could be chlorine, bromine, or iodine, okay? And essentially what happens is one of your fluorines here, it's going to substitute for one of the hydrogens on your alkane. And so we can see over here that now on the product side, one of the fluorines is now attached. And so this is a halide or a halogenoalkane is the other name that we learned for this. And then your other product is that hydrogen that the fluorine replaced, it bonds to the other fluorine. And so you essentially make, an acid. So hydrofluoric acid, but we don't really call it that. We just call it the regular name that it's known by, which is just hydrogen fluoride. So if we look at some of the practice ones for this one, we're going to kind of go through them. So if you want to kind of pause and try, that's what I recommend doing, is pause and try to do them on your own first. And then you can unpause and kind of watch us go through them together and check yourself. So this first one over here, practice 84, it says, which substance will likely undergo a substitution reaction with iodine? So again, keyword here is substitution, okay? And with iodine. So it's a substitution with a halogen, and the only thing that can do that are alkanes, like we said up here. So essentially on this one, really all you need to do is look at the names of the substances. There is only one that ends in ANE, like an alkane, and that is here, that's number 3. This one is ENE, so that one is an alkene. It's got a double bond, so it can't do it. This one's got the OL, that's an alcohol. And this one's got the YNE, that's an alkyne with a triple bond. So the only one that is an alkane with all single bonds and saturated is this one, number 3, and we can tell that by the ending of the name, okay? So practice 85, which equation represents a substitution reaction? So again, on something like this, really we just got to remember this pattern. So we're going to have an alkane reacting with a halogen, and in our products are going to be a halide or a halogenoalkane and an acid. So it's hydrogen paired up with whatever the other halogen was. So if I look at the answer choices here, it's pretty obvious that I could eliminate number 1 and number 3. And the reason I can eliminate those is because if I look, they don't even have 2 products, okay? Our pattern up here, we have to have 2 products, the halide and the acid. So I can eliminate those 2, okay? I can also eliminate number 2 because that's oxygen is not a halide or a halogen, excuse me. And so can't be number 2 because number 2 doesn't have a halogen in it, okay? Number 1 didn't either, but we already eliminated number 1 based on the only having 1 product. So that leaves us with number 4, which is correct. So I can see CH3CH3, that's a saturated hydrocarbon because if I were to draw out the structural formula, the full one, since each carbon has 3 hydrogens attached to it, that means that this has to be a single bond, okay, to not violate the octet rule. And then it's reacting with a halogen, and then I can see now the halogen, one of the halogen atoms is attached to this carbon, the hydrocarbon, and then the other one is bonded with the hydrogen that it substituted, okay? So that's the only one that follows the pattern of our reaction from up above. All right, number 86, draw and name the structural formula of the organic product. Okay, so some keywords here: product and organic. Okay, so product means it has to be on the right side of our equation, and then it wants the organic product specifically. So that's not going to be this one because it has to be something that contains carbons and hydrogens, right? If it's organic. So that means that they want us to draw and name the structural formula of this compound. And so if I look here, I have 1, 2, 3, 4 carbons in the main chain. I'm not going to count this one because it's in parentheses. That means it's a branch coming off of the main chain. So I have 4 carbons in my main chain. I can see that there's an I that's going to be on this first carbon because it's listed after the hydrogens that are attached to that first carbon. So I'm going to stick an I on the first carbon. And then this one in parentheses, it's a branch coming off of this carbon that it's right in front of. So that's the third carbon in the chain. So that means that there is a CH3 branching off of that third one. And then everything else is going to be filled with hydrogens to complete octets. So I need a couple hydrogens here. I need a couple hydrogens here. I need one here. And then this one on the end is going to have 3 hydrogens. So that's what my complete structural formula would look like. And then for as far as the name, I can see there's 4 carbons in the chain. So it's going to be butane. It has a halogen here on the first carbon. So that is like 1 iodobutane. But there's also a methyl group branching off here of the third carbon. So I would say it's 1 iodo, 3 methyl, and then butane. Okay, that would be the correct name for that one. All right, 87, draw and name the structural formula of the product that will form. So this one's a little tougher because they're not giving us the formula of that organic product. We got to predict it, okay? So again, go back up here to your pattern. You have an alkane, you have your halogen, so you know your 2 products are going to be the halide or the halogenoalkane and the acid. So they've given us the acid, okay? We're missing the halide or the halogenoalkane. So essentially what I just need to look at is I need to look at the fact that, okay, I see 5 carbons in this chain, and I know that with the chlorine, one of them is going to switch with one of the hydrogens. Most likely it's just going to do one of the ones on the end, so you can just pick one end and stick it on there. But essentially, if I do draw my 5 carbons out, and then I'm just going to replace this one on the end with a chlorine, and then everything else stays the hydrogens just like it was before. So we're just substituting one of those hydrogens for whichever our halogen is. In this case, it was chlorine on this one, okay? So then, as far as the name, we see 5 carbons in the chain, so that's going to be pentane. There's no branches, but then we do have the chlorine coming off, so that it's going to be 1 chloropentane. All right, moving on, our second type of reaction, these are called addition reactions. These are reactions that alkenes do. Alkynes can also do them, but it's not as often. So we're going to focus on the alkenes for our reactions. And the addition, there's 2 sort of subtypes that we need to know the name for. The first one, it's called hydrogenation, is sort of the scientific name. That's the name that IB uses. Hydrogenation means that you're adding hydrogen to the double bond in order to break it and to make it saturated. So essentially, it says here in hydrogenation, hydrogen atoms are added to a double bond of an alkene, and the unsaturated alkene is then changed to a saturated alkane. So an example down here, I can see that I have an alkene. It's unsaturated, meaning it's going to have, a multiple bond somewhere in it, at least one. And I'm reacting it with hydrogen. So here is my example. I have propene, okay, 3 carbons in a row with a double bond. And then here's my hydrogen. And then what happens is this double bond gets broken. And when it gets broken, that means that each of those carbons can bond to something else to complete their octet. And so we add a hydrogen atom onto each one so that they have a complete octet. And so our product ends up being an alkane that is now fully saturated, and it has all single bonds on the carbon chain. So that's the basic pattern here is something with a double bond reacts with hydrogen, and you end up with an alkane with all single bonds, and the hydrogens have been added onto the molecule. The other type of addition reaction is called halogenation. That's the term IB uses. And it's basically where we're, instead of adding hydrogen like the first one, we're adding a halogen, okay? So the difference between this one and the substitution that we saw up here is that for substitution, we have two products. We're just substituting one halogen atom for a hydrogen and then also producing an acid, okay? For addition with halogens, for halogenation, we're not, if you look over here, there's only one product. So we're literally adding the atoms of the halogen onto the molecule in order to saturate it and make something that has all single bonds. And so it kind of follows a very similar pattern to the hydrogenation. The only difference is instead of H2 here, we have one of our halogens, bromine, chlorine, iodine, fluorine, okay? But the same thing's going to happen in that the double bond here is going to break. And so each of the carbons that were on that double bond are going to gain one of the halogens. And so when we do this, we end up, our product ends up being a halide. Specifically, it's a dihalide or a dihalogenoalkane because it has two halogens now attached on it. And so if we were to kind of do the name for this, this one would be 1,2-dibromo because it's a dihalogenoalkane, and then propane because of the three carbons right there. So the practice for this one, and again, if you want to kind of try to do them on your own, pause now and then come back and see if you can check your work after you've attempted them. But I'm going to go ahead and start with practice 88 here. Which substance will likely undergo addition reaction with iodine? Okay. So an addition reaction means that it has to be something that is unsaturated. It cannot be an alkane. So the easiest thing to do on this one is, since they give us names, is to look at the names. We're looking for an alkene or an alkyne, something that has a double or a triple bond in it. So automatically I'm eliminating both 3 and 4 because they are already saturated. They're already alkanes. They end in A and E. And then same thing, if I look at the names over here, this one on number 2, it ends in the O-N-E. That's going to be a ketone. That's not an alkene or an alkyne. So the only one that has an E-N-E ending is number 1. So that would be able to do an addition reaction with iodine, which is a halogen. Practice 89, which equation represents an addition reaction? Okay. This should be fairly easy because I told you guys if we compared sort of these addition reactions to the one up here for substitution, then the most obvious difference is that for addition reactions, you only have one product. Okay. And so if I look at the answer choices here on 89, all of these have two products, so they cannot be it. It has to be number 1. Okay. The other thing that you can tell, so like let's say we had 2 of them that they had one product and we weren't sure. Look at the formula of your reactant and your product, your organic ones. This is obviously an alkene because it's following that N and 2N ratio for the subscripts, which means it's got to have a double bond. It's got to be an alkene in that homologous series. And then the product C2H6, that's following the pattern for an alkane because remember it's 2N and then plus 2 to get the number of hydrogen compared to carbon. So all those things that we've talked about in the past, it's why it's important to remember that, because it can make it really easy to quickly kind of be able to answer something like this and not spend a lot of time thinking about, well, which one is which and that kind of stuff. All right, on number 90 over here, draw and name the organic reactant. So again, keywords here, reactant, meaning it's got to be something on the left side of our arrow for our equation. And then organic, meaning it's got to be something that contains carbon, okay? So keeping that in mind, the organic reactant is this one right here, okay? And so if I'm going to draw out the structural formula, so I can see there's 1, 2, 3, 4 hydrogens in my chain. So 1, 2, 3, 4. The first one got 3 hydrogens. Second one has 2 hydrogens. The third one only has 1 hydrogen. And then this one over here has 2 hydrogens as well. Okay. So looking at that, if I draw that out, I can see that there's clearly not a complete octet with these 2 carbons over here. So I'm going to make a double bond because otherwise I don't have any more hydrogens to add. So drawing that out and then now being able to name it, there's 4 carbons in a row. So that's going to be bute. And then there's a double bond, so it's butene. And then if I want to be specific, because the double bond starts on the first carbon, if I start numbering from right to left, like 1, 2, 3, 4. So it's 1 butene. Okay. All right. So then last one for this section is 91. Draw and name the structural formula of the product that's formed. So again, this is one where we have to figure out the product first. So if I look here, I can see I have a hydrocarbon with a double bond. So it's an alkene. I'm reacting it with a halogen. So again, this is where you want to start to see these patterns where, oh, it's a double bond, it's an alkene, and it's reacting with a halogen. So it has to be this type of reaction. It has to be halogenation, okay? And so essentially what's going to happen here is if we follow the pattern just like up here, then this double bond is going to break, and then the 2 fluorine atoms are going to attach onto those 2 carbons that were where the double bond was located. So if I draw the product, 1, 2, 3, 4, 5 carbons, they're all going to be single bonded now. Everything, the hydrogens will still be all in the same spots like they were. But now, wherever that double bond originally was, now we're going to have the 2 fluorines attached, okay? And so the name for this one, it's going to be pentane because it's 5 carbons all in a single bonds, okay? And then we have to account for the 2 halogens, the 2 fluorines. So it's going to be 2,3-difluoropentane. Okay, I kind of ran out of room, had to kind of squish that there. But 2,3-difluoropentane because the fluorines are attached on the 2nd and 3rd carbons of the chain. All right, next type of reaction. This one is called esterification. And so, you can see in the name, it's got ester, which is one of our functional groups that we've talked about in the past. And so that's kind of gives you a hint about what this reaction is going to do, because this type of reaction is where we react an organic acid. Remember, those are also called carboxylic acids, okay? So when I react an organic acid or a carboxylic acid with an alcohol to make an ester. And so because we're producing an ester, it's esterification, okay? And that's essentially what this sentence says underneath here. I'm not going to read it again. The only thing I'm going to point out is that the alcohol has to be a primary alcohol. So we talked previously about the fact that alcohols can be primary, secondary, or tertiary, depending on the number of carbons that they're attached to. So if the OH is attached to a carbon that's attached to one other carbon, it's a primary alcohol. If it's attached to a carbon that's attached to 2 other carbons, it's a secondary alcohol. And if your OH is attached to a carbon that's attached to 3 other carbons, then it's a tertiary alcohol. So for esterification to work, it has to be a primary alcohol. It cannot be secondary or tertiary. And so what happens is you will form an ester, but you also produce water. So water is also formed. And the reason it's formed is because the hydrogen ion from the acid and the hydroxyl group from your alcohol, they come together, and that H plus OH makes H2O, okay? So here's an example. So here's my carboxylic acid or my organic acid. Here is the full structural formula. This one is specifically ethanoic acid because it's got 2 carbons here. And then it's reacting with an alcohol. In this case, I can see here's my hydroxyl group attached to my carbon chain. It is a primary alcohol because if I look here, the hydroxyl group is attached to this carbon, and that carbon is only attached to one other carbon. So that's a primary alcohol. And this one is propanol because it's got 3 carbons in the chain. So if I know that, okay, my reactants, one of them is an organic acid, one's an alcohol, then I know it's going to follow this pattern. And so what's going to happen is the hydrogen from the acid, this hydrogen ion is going to end up breaking off, and it is going to bond with the hydroxyl group, and it's going to form water. HOH makes H2O. And so then what happens is the oxygen here, it ends up bonding to the carbon here to make sort of one long chain, and so we end up with an ester because I can see over here I have that double bonded O and single bonded O on the same carbon. And so that is what the functional group for an ester, okay? So this one, we had ethanoic acid, it reacted with propanol, and our product is propyl ethanoate. And so just to kind of clarify about the name part, because you know that when we name an ester, okay, the double bonded O, however many carbons it's attached to, that's the main part of the name with the OATE ending, okay? So because on this example, it's attached to 2 carbons, that's ethanoate, okay? And then the front part of the name, the prefix part, comes from however many carbons are attached to the single bonded O. And so this one's got 3, so that would be propyl, okay? So propyl ethanoate. So the thing that was clarified down here is that the first part of the name, in this example, the prop, it comes from the alcohol. So the first part of the name will always come from the alcohol, in case you didn't figure that out, propanol. Okay, so it's propyl. And then the second part of the ester's name, which in this case was the ethanoate, that eth came from the organic acid. So if we notice, it was ethanoic acid. And so it's always going to follow that pattern where that first part of the name is going to come from whatever the alcohol chain was. And the second part of the name is going to come from whatever the name of our original acid was. So now looking ahead to practice, again, try to pause, try to do some of them on your own before you start checking and going ahead. But I'm going to go ahead and start working, so pause now if you want to. So on this first one here, practice 92, it says a structure of which organic compound is a product of a reaction between an organic acid and alcohol. So basically, they're asking which of these structures could be formed if you reacted an acid and an alcohol. So if we know that the pattern is an acid plus an alcohol makes an ester and water, then we know that we're looking for something that has an ester functional group. And so if we look at all of the answer choices, the only one that has an ester functional group is number 1. It has this double bonded, single bonded O on the carbon. This one, those are hydroxyls. Those are some alcohols. This has one O, but it doesn't have the double bonded O, so that's just an ether. And then this one doesn't have any O's at all. This one's just a halogenoalkane. All right, number 3, which compound will react with methanol to form methyl propanoate? So again, this goes back to sort of this last little note here, is that the first part of the ester's name is going to come from the alcohol. So if I have methanol, the methyl came from that. So in order to figure out the other compound that reacted in order to make this, I need to look at the name part of the second one. So it's propanoate. So that means it has to be prop, okay? And it has to be the organic acid, okay? So in this case, it would have to be propanoic acid for it to make that ester. All right, 94. Draw and name the organic substance that reacts with ethanol in the reaction shown below. So here is my ethanol. So I can see 2 carbons, got the hydroxyl group there. And then if I look at my product side, I can see that I have water and I have something that it's an ester because I can see that functional group right here. So the alcohol, okay, that I had originally, that alcohol is here, okay? So remember the oxygen is the hydrogen is what's going to come off, the OH, the hydroxyl group, is what's going to come off to help form the water, okay? So that, so our ethyl over here comes from that alcohol. So to figure out what the original other reactant was, I need to look at the other side. So if I look here, I see that there's 4 carbons that double bonded O is attached to. And so that means my original organic substance had to have 4 carbons with a double bonded O and then the other single bonded O. So all of this that I'm about to highlight, this is all from the original other reactant, which in this case is an organic acid or carboxylic acid. And so if I kind of draw that out, I know that I have CH3, CH2, CH2, and then C, double bonded O, and then it'll be OH, okay, because that's got to be that hydrogen that was from the original organic acid. And so then the name for that, if I looked, It's got 4 carbons, so it's bute. But even if I don't know that, I can just count the original 4 here and know that, it's got to be bute. And so in this case, it's butanoic acid. And then the name, I forgot the C. There we go. And so then the name of this, since the first part would come from the name of the alcohol, this would be ethyl. And then the second part of the name would come from what's highlighted in that kind of yellowy green that had the 4. So it would be bute. So butanoate. So ethyl butanoate would be the name of that product, even though they didn't ask for that on the question. Okay, 95. Draw and name the structure of the organic product that will form in the reaction below. So again, if I look at my reactants, I should kind of look for functional groups. That's a carboxylic acid or an organic acid. This is an alcohol, okay? And so again, I got to know that if I have a carboxylic acid and an alcohol and they react, that is this type of the esterification. So my product's going to be water and whatever ester is going to form based on my carbon chains. So if I look, this one I only have 1 carbon, but over here I have 5 carbons, okay? And so what's going to happen, if you remember from the example up above, is the hydrogen ion here from the acid is going to pair up with the HOH. So that's where the water came from. And so that means that this carbon here, it's going to bond to this O on the other chain. And so I'm going to end up with 1, 2, 3, 4, 5. There's my double bonded O, my single bonded O, and then I'm only going to have 1 more C connected because this other reactant only had 1 C. And then everything else would get filled in with hydrogens, just like always, to complete the octets of all of the elements, all the atoms. The only one that we're not going to add any on is the single bonded oxygen. We don't ever add anything extra on that. There are probably some lone pairs, but we don't really draw them. We don't really indicate it. So then to know the name, now we got to go back up and kind of look at the pattern that we did. So remember the first part of the name comes from what was the alcohol. And so this alcohol over here, this was methanol. So here this is methyl. And then the second part of the name comes from the organic acid. So this was 5. So that's pentanoic acid. And so this would be pentanoate. So methyl pentanoate. All right, next type reaction. This is another one that's got sort of 2 subcategories, like the addition one earlier. Polymerization. So poly means many. And so essentially what we're doing with polymerization is we're joining small organic molecules to make longer ones or bigger ones that have a lot of repeating units in their patterns, okay? And so that's basically what it says here. We join small organic compounds, small organic molecules together, make a longer chain. And so we have some kind of terminology here. The small unit molecules, the small individual unit ones, they're called monomers because they're only 1 unit, okay? What happens is you have monomers and then you can join them together with their bicovalent bonds and you create a polymer because it's got multiple or many of your units repeating. So the 2 types of polymerization reactions that we need to be aware of, the first one is called condensation polymerization. And this is where you join small molecules by removing water. And so water is going to be one of the products, like I can see right here. And so if you think about it, condensation, if we think all the way back to like states of matter and phase changes, condensation is the change of state where you form a liquid from a gas, right? The gas turns into a liquid, right? And so essentially what's happening here is that we're forming liquid water, even though we might not have had a liquid. We might have had gases and things like that. They could be liquids in the beginning, but it's condensation because it kind of has to do with the fact that we're forming water, okay? So what happens in these is you have monomers with hydroxyl groups. So they're going to be alcohols. So these examples, there's methanol and ethanol. And then they're joined together as water is removed. And so what happens is the hydrogen from one and the hydroxyl from the other, they kind of pull apart and they make water. And then what happens, what's left is this O that will single bond to the C and it will make an ether, okay? And so ethers are one of the substances commonly produced by this type of polymerization. The other one is proteins. And so this is where we sort of see like biology and chemistry starting to overlap a little bit more because proteins are polymers. They're just long chains of repeating units. And so they can be created by bonding, a couple of different monomers together. The other type of polymerization that we need to be aware of, it's called addition polymerization. And this is where we have small unsaturated molecules. So remember, unsaturated means that we have a double or a triple bond somewhere, okay? And so we join them together in like repeating units over and over and over and over. And so because it's repeated over and over, we don't really always use numbers to represent them. We use the sort of placeholder N. And N represents several repeated units. Like it could literally be like 35, 100, 24, okay? But it's usually a big number. And so what happens here is you have identical small alkene molecules with a double bond, okay? And so if I look at the example here, the monomer that they're using is ethene, okay? So it's got 2 carbons, right, double bonded. So it's ethene, that double bond. So what happens is when I make the polymer, this is how I visually represent it. If you notice, it's still CH2, CH2, but now it's single bonded. But look, they each have sort of a bond coming off the side now that's sort of inside these parentheses with the N down here as a subscript. What I'm doing is I'm saying when I form this polymer, I'm breaking this double bond. And so each of these is now going to bond to something else on the other side. So that's why I draw those bond lines in there to show that their octets are going to be complete. Because what's really going to happen is I will have that CH2, but then there will be another CH2, CH2 over here. And so like this one and this one, they're going to like bond together. And so you're just going to have repeating units of CH2s, like over and over and over, okay? So some common polymers that are produced by like natural and synthetic are listed below. So natural polymers happen from the first type of reaction, the condensation polymerization. So these happen naturally. And a lot of them are things that take place in, plants, animals, humans, things like that. So forming proteins, forming starches, and forming cellulose, like in plants. All of those things are going to be polymers that are created by doing condensation polymerization and getting rid of some water in order to create a polymer. The other type are synthetic. So these are like man-made or lab created. They're not naturally occurring. These occur by doing the other type, the addition polymerization. So these are things like nylon, any kind of plastics are made this way, polyethylene and polyvinyl. So those are things that are used for like different kinds of like tubing, building materials, things like that. And then obviously like nylon is used in, materials for fashion design, clothing, that kind of stuff. All right, so this practice for this one, it says, given the incomplete reaction below, draw and name the organic product of the reaction. So again, try to start, see if you can do it on your own using the guides up here as, or the notes up here as a guide. But if I look at my 2 reactants, okay, I can see that they're both alcohols. Okay, they both have hydroxyl groups. And I can see that I'm producing water. So this is really a clue here, is that if I'm producing water and I have 2 reactants that are both alcohols, this is going to be this condensation polymerization. Because that's the only one where I have 2 alcohols and then one of the products is water. My other one's going to be the ether based on my 2 reactants, okay? So if I kind of come back down here, I know that the H and the OH, they had to pair up to make this water. So what's left, if I kind of redraw it out, is there's 2 carbons, and then that's oxygen, and then it's going to bond to this other side that's got 4 carbons. So 1, 2, 3, 4. And then obviously everything will get filled in with hydrogens to complete octets on here. For the carbons, not the oxygen. That stays like it is. All right, So we got all of our hydrogen filled in. So we've drawn it. So we know it's an ether. Okay. I should know it's an ether because it's got that single bonded O. And so I need to think about how to do the name. And really, I just look at the number of carbons on each side of that oxygen. It's in the chain. So on this side, you see 2. So that would be ethyl. And on this side, I see 4. So that would be butyl. So this would be ethyl butyl ether. All right, next type of reaction, and we're not going to go into a lot of details on these, just that you need to know like sort of the basic patterns and process and how to recognize them, and sort of what, if you have this reactant, what product could you make, and that kind of a thing. So the first one is fermentation, and this is where you make ethanol from sugar. And so you make ethyl alcohol or ethanol from sugar, and then carbon dioxide gas is also produced. Okay, so you'll see like bubbles getting produced and things like that. In order for fermentation to occur, you have to have a catalyst that's known as an enzyme in order to kind of start the process. So here's our basic pattern. You have some kind of sugar. It starts to break down because in the presence of an enzyme, and it ends up making an alcohol, ethanol, and carbon dioxide gas. Okay, so an actual example would be this one. So I have glucose, that's a sugar. And then the enzyme that's participating is called zymase. Anything that ends in ASE is an enzyme, if you don't remember that from biology. And then if I look here, my product, I can see there's an alcohol, and I can see carbon dioxide, okay? So again, and it's ethanol, I can see it's C2H5OH. Okay, if I draw it out, it looks like this. So that's the basic pattern, is you have a sugar, and when it's in the presence of an enzyme, it will start to break down and make that ethanol and give off carbon dioxide gas. This next one, this is called saponification. This is the reaction that happens when we make soap. And so in order to make soap, your two reactants, you have to have something that's a fat and something that's a base. And so remember, bases are things like NaOH, KOH, okay, things like that are hydroxide. So sodium hydroxide, potassium hydroxide, calcium hydroxide, that kind of stuff. And then your products, one product is going to be the soap. The other product is going to be an alcohol. Specifically, it's going to be called glycerol. Now, glycerol is not its actual chemical name. If we were to name it properly, if we look, it's got 3 carbons, so it's prop. And then because it's got 3 hydroxyls, it's 1, 2, 3. And then propane triol, because it's got 3 of the alcohols, 1 on each of the carbons. So glycerol is more of its common name. It's kind of like how we call water and not dihydrogen monoxide, because it had a name before our official naming rules went into place. And so a lot of times we just still refer to it as water. Just like this one, we would refer to it as glycerol. But know that these are the same thing, okay? All right, combustion. I think this is our last type that we're going to talk about. So combustion is where you burn an organic substance with oxygen. And so this is one that we actually talk about in first year chemistry. We don't really relate it to organic, but we do talk about that it is one of the 5 basic types of reactions that we learn in first year chemistry. And so you have an organic compound. Usually it's a hydrocarbon. It could be an alcohol. It could be something else, but most of the time it's usually just a hydrocarbon. And we burn it or react it with oxygen, okay, O2. And the products are always going to be carbon dioxide and water, as long as we have an excess of oxygen, which for right now, we're going to assume we do. Eventually, we're going to talk about next year, like what happens when you don't have enough oxygen, because then you don't produce carbon dioxide water. You might produce carbon monoxide and water, or just elemental carbon and water. Okay, it depends on the situation. But for right now, this is sort of our pattern, is that we have some kind of organic compound. We're reacting with oxygen, and we're producing carbon dioxide, gas, and water. Okay, and so they all follow kind of this basic pattern that we can see here. This one specifically is octane, which is the main component in gasoline for cars. It burns in your engine in your car when you start the motor, and it heats up and gets going. It starts the spark, and so it burns the fuel from the gasoline, the octane, and it produces carbon dioxide gas and water, and that carbon dioxide gas is what helps to sort of propel the car and make the wheels move and all that kind of stuff operate. So this next page, really, this is a summary table. So if you're trying to do, when you're doing your practice later on, this is a quick or a good thing to use to quickly look for the patterns that we talked about. So like substitution, your reactants are going to be an alkane, all single bond saturated, and a halogen. And then you have two products that are listed here. For addition, we have the two subtypes, hydrogenation, halogenation. And so the difference, they both have alkenes. The difference is obviously hydrogenation, you're reacting with hydrogen. Halogenation, you're reacting with a halogen. And so the products here, we get, there's only one product, and we get either an alkane for hydrogenation or a dihalogenalkane or a 2-halogen halide, okay, for halogenation. For saponification, we start with a fat and a base. Remember, a base is something that's got OH that's not organic. So like a metal hydroxide, like sodium hydroxide, potassium hydroxide. And we produce glycerol, which is really, its name is 1,2,3-propantriol. And our soap, that's our actual product that we're trying to make. For fermentation, remember this one requires an enzyme because it only has one reactant, so it has to have that enzyme to start breaking down. And so we have sugar, and it breaks down with that enzyme, and it produces ethanol and carbon dioxide always. It's always going to be the same. For combustion, we have a hydrocarbon, so typically it's some kind of carbon-hydrogen compound. We don't know the subscripts, but it could have oxygen in it. It could be an alcohol or something else. The other reactant, always oxygen gas, and our products, always carbon dioxide and water. Esterification, this is the one where we start with a carboxylic acid or an organic acid, react it with an alcohol, and we get two products. One's an ester, and then the other one is the byproduct is that we get some water. Polymerization, we have two kinds that we talked about, the two subgroups. For condensation polymerization, that's where the one we focused on is where we had two alcohols, and those are our monomers, and they join together to form a polymer. And with the alcohols, it's always an ether. And then there's some water produced because it's that condensation polymerization. The other one that we didn't really talk about in the examples, other than just mentioning that proteins are made this way, is we can have an amino acid react with another amino acid. Those would be our monomers. And so our product is a protein. That would be the polymer in this case. So we have repeating amino acids attached to each other. And then it also still produces some water. The other one, the addition polymerization, this is where I have some kind of monomer, okay, with a double bond, like ethene, could be propene, I don't know. And essentially what happens is we break that double bond, and then we allow each of them to bond to another ethyl group on the sides. And so instead of just ethene, now it's polyethylene, which is the name for that polymer. This last one we didn't really talk about, so I'm not going to go into it in detail, but there is another one called cracking, and it's where you have a really long chain hydrocarbon. Like I can see this one's got 14 carbons in it and 30 hydrogens. And what happens is you essentially break it down. You crack it or you break the chain. And so you end up with a couple of different carbon chains that are just shorter, okay? All right, so again, I'm going to start going through the practice, but again, I would, advise you to maybe pause, try to do some of them by yourself before you start checking. But I'm going to go ahead and go through it. So on number 97, which reaction is used to produce polyethylene from ethylene? So things to look for here are like, what do we see in the names? Okay, the biggest thing that I can see is right here, polyethylene. So it has to be polymerization because that's the only one that has that in the name. So it can't be 3 or 4. So, but then we had two different types of polymerization. Is it addition or is it condensation? Okay. Well, if we look at what we're making, we had an alkene and we made a polyethylene. Okay. So if I come up here to my two types of condensations, this one up here, I had to have two alcohols or two amino acids react. And that's not what I have. They told me that I have ethylene, ends in E and E. And so that's going to be the addition one because I have some sort of, ethene, some sort of monomer that's got a double bond, so it's going to end in E and E, and I end up producing, the whatever the polymer is, so polyethylene, that kind of a thing. So it has to be number 1, addition polymerization. All right, 98. Carbon dioxide and water are two products formed from which organic reaction? So again, go back up and look at your patterns of your equations. The only one that has carbon dioxide and water as the only two products is combustion. And so that would be number 1. All right, 99. Chloromethane is likely a product of, and then it wants to tell us which type of reaction. So my product is an alkane, which means it's saturated, it's got all single bonds, and it's a halogenoalkane or a halide because it has the chloro. And so if we think about the different patterns, it can't be fermentation because fermentation is where we had the sugar and we made alcohol and carbon dioxide, I believe. Neutralization, we didn't even talk about that word. So it's got to be a 1 or 3. So then if I go back up and look at my patterns, okay, for substitution and addition, the only one that produces something with a halogen attached is this one. This one does, but it's got 2 halogens attached, not just 1. And so the one in question only has 1 because it's just chloromethane. It's not dichloromethane. And so that means it would have to be, most likely it would be substitution, not addition. All right, practice number 100. So consider the equation below. What can we describe this type of reaction as? So if we look here, I have C5H10. I'm reacting it with hydrogen. I get C5H12. So first thing is there's no oxygen here, so it's definitely not combustion, okay? There's also no sort of repeating patterns. I don't see like any of the ethers. I don't see anything that's like the N with the repeating numbers. So it can't be polymerization. So it's either hydrogen addition or hydrogen substitution. And so if I go back up and look at my little chart here, my little cheat sheet, substitution, I have to have 2 products. Addition, I only have 1 product. So just by that alone, I should be able to say, oh, well, it can't be substitution because substitution would have 2 products, and it doesn't. So it has to be hydrogen addition. The other way that you can kind of figure that out is if you remember your patterns for your hydrocarbon formulas. So C5H10, that's twice as many hydrogens as carbon, which means that that's an alkene, meaning it's got a double bond. And so if we react something with a double bond with hydrogen, it's going to break that bond and saturate it. And so we can see here now, C5H12, that's the pattern for an alkane, where it's all single bonds. And so if you know those numbers and those patterns, you don't even really need to like draw anything out. You can just be like, all right, this is an alkene based on the numbers. And so it's reacting with hydrogen. That's hydrogenation or hydrogen addition. And I get an alkane because I see that number 12, that pattern of 2N plus 2 there. All right, 101, the organic reaction below can be described as, and they give us 4 different types. Okay, so if I look at my different functional groups and what I got going on here, I see an OOH, so that's an organic acid or a carboxylic acid. I see OH, so that's an alcohol. And then over here I see water as a product, and then my other product, I have this OO in the middle. So that implies that one of them is double bonded and the other one's single bonded over here. And so that is an ester, okay? So if I look at, I have an acid plus an alcohol, and my products are an ester and water, it should be pretty easy. If I'm producing an ester, it's esterification. All right, the reaction below is an example of, and so look at the patterns of the reactions, guys. So again, hydrocarbon, fuel, reacting with oxygen, water and carbon dioxide are the products. That's combustion reaction. All right, 103, the reaction, and they give us kind of this reaction with the structural formulas drawn out, is best classified as, and then it wants to know which type this is. So let's look at the reactants. So I have, both of them are alcohols, okay? They both have hydroxyl groups. And so if I look at the products, I got water, and then I have an ether. And so this is probably an example of where the hydroxide of one is going to bond with the hydrogen on the other, and it'll leave this oxygen here to connect them to make the ether. So then if I look at what's on either side, well, not what's on either side, but if I look here and I know that it's an ether, and I look at my, back up at my pattern, so I have 2 alcohols, and I made an ether and water. That is right here. That's the condensation polymerization. That's the pattern it's following. And so polymerization, they didn't ask us if it was condensation, but just polymerization on that one. All right, last page of practice. So these are the ones where they're going to show us some information and have us answer a few questions, not multiple choice. So for this first one, we're going to use, for these first three questions, actually, we're going to use this first structure, the first reaction. So this is a reaction between bromine and a hydrocarbon is presented by the balanced equation below. Write the name of the homologous series to which the hydrocarbon belongs. So the hydrocarbon is this reactant right here. That's the only molecule that has only carbon and hydrogen. So the homologous series, well, if I look, the only functional group it has a double bond, which is an alkene. So that would be the homologous series would be the alkenes because they have double bonds. Then the next thing says to write the name of the product. So the product is over here on the right side. So I can see there's 3 carbons. So that's going to be prop. And then they're all single bonds. So it's going to be propane. And then I see that I have 2 bromines attached here. So it would be 1, 2, dibromopropane would be the full name for that. And then the last one is says identify the type of organic reaction represented by the equation. So again, go back up to that cheat sheet page of the pattern. I have an alkene and I'm reacting it with a halogen, and I ended up saturating it and attaching both of the halogen atoms. So this would be halogenation, which is a type of addition. So addition is like the main class, but specifically it's a halogenation type of addition reaction. All right, next 3, we have a new equation here to look at. So it says the unique odors and flavors of many fruits are primarily due to small quantities of a certain class of organic compounds. The equation below represents the production of one of these compounds. So we have reactant 1, reactant 2, product 1, product 2. So the first thing is, before we even start going through, let's see if we can at least classify what these are. So reactant 1, I see this functional group here, OH, that's an alcohol. Reactant 2, I see a double bonded O and a single bonded O. That is an ester, okay, double bonded O, single bonded O. And so then if I look, my products, I have this kind of connected here, okay? And then I have water. So it says state the class of organic compounds to which reaction 2 belongs, and I realized that I just told y'all the wrong one. This is not an ester. It is a carboxylic acid. Okay, which is the answer to number 107. So it's either organic acid or carboxylic acid. And again, I can tell that because I have the double bonded O and then the OH functional group there. 108, identify the type of organic reaction represented by the equation. So again, if you have an alcohol and you react with a carboxylic acid or organic acid, you produce an ester and water. And so when you produce that ester, it is esterification. All right, last one for here. Draw and name a structural formula for an isomer of product 1. So product 1 is this one right here. And so if I kind of think about what the molecular formula is of that, I see 3 C's. So C3, H, 1, 2, 3, 4, 5, 6. And then O2, okay? So it has to be something that has this same molecular formula, but a different structural formula. So kind of the easiest thing to do first would be to, kind of just shift the oxygens over onto the second carbon instead of the first. And so I could do that by having like C, and then my O's would be coming off of there. And so if I did that, the name for this one, because it is an ester, okay? And so if we remember for our esters, the double bonded O, that part of the chain is, I believe, the main one. Let me go back up here just to make sure I'm not going to tell you all the wrong thing. There it is. Okay. Yeah, the double bonded O is the main part of the name. So yes. So if we go back down here now. So the double bonded O is attached to 2 carbons. So that is ethanoate. And then the single bonded O here is only attached to 1. So this is methyl. So methyl ethanoate, which originally this one up here, this was ethyl methanoate. So they were flipped, okay? Another example of an isomer that we could do for this one, so we still need 3 carbons, okay, and 6 hydrogens. So I'm going to do 1, 2, 3, 4, 5, complete our text. But then that leaves me with 2 oxygens and a hydrogen. So what I could do is I could double bond oxygen here, and then I could do an OH, and now that is a carboxylic acid. That would be propanoic acid. Propanoic acid. And again, it still has 3 C's, 6 H's, and 2 O's. So it follows that it is an isomer. All right, last 2 down here. One type of soap is produced with ethyl stearate and sodium hydroxide react. The soap produced by this reaction is called sodium stearate, and the other product of the reaction is ethanol. This reaction is represented by the balanced equation below, so they show us sort of the structures drawn out and labeled. First question, to which class of organic compounds does ethyl stearate belong to? So if I look here at this molecule here, even though that's a weird name, we're not really sure, all I got to do is look for functional groups, guys. So I see a double bonded O and a single bonded O. That means that it's an ester, okay? The second one says identify the type of organic reaction used to make soap. So this is just a straight up vocabulary. So it's saponification. All right, so that is it. That's it for the practice and within the notes. So you guys have your worksheet for 47 to be working on, and that's our last grade for the semester. So if whatever you have done, make sure you get it turned in today from lessons 43 through 46. And then 47 will be the only thing that you'll be able to turn in next week on Tuesday. If you get it done today early, go ahead and turn it in. But if not, you can turn that one in on Tuesday.